Pod 1, give me one thing that you discussed. Okay, so it looks like it's probably some sort of cubic function. On Monday, we'll do an activity to talk about some transformations. And then in chapter 2, we'll be able to know like what the equation of this is and do a lot of that kind of work. Good. Pod 2.
We have the relative minimum of 2, -2, and then the max is -1, 3.
So 2, -2 was a relative minimum. And you said the max, a relative max was here at -1, 3? Okay, how does that sound? We go from increasing to decreasing for our max, decreasing to increasing for our relative min. Pod 3, something else.
Domain is all reals.
Ooh, our domain is all real numbers. Can you tell me how to notate that?
Infinity, comma, negative infinity.
Okay, I'm actually going to put the -1 first since it's smaller, right? So negative infinity to infinity. We say it all real numbers, but that's how we notate it in integral notation. Very good. Pod 4. Okay, so we have zeros. I'll highlight those in blue right here. Okay, so those are our zeros. You said -3, 1, and 3. Excellent. Pod 4, anything else to add?
It increases from negative infinity to -1.
Okay, so we'll do that in black. So it increases from negative infinity to -1.
Mm-hmm. And from 2 to infinity.
And from 2 to infinity. And since there's 2 of those, we can union those together. So from negative infinity to -1, and then from 2 to infinity, we are increasing. I like it. Pod 6, anything to add?
We're decreasing from -1 to 2.
We are decreasing from -1 to 2. I like it. Pod 7.
I don't think we had anything else.
Did you identify the domain? Did you identify something else?
The range.
Okay, the range you're saying is all real numbers. Okay. And really, that's everything we talked about yesterday, right? Perfect amount. Yes. I want open intervals for increasing and decreasing because if we think about it, like here at x is 2, we're switching directions. So we don't want to include 2 in increasing and we don't want to include it in decreasing. Okay, so increasing and decreasing are always open intervals. Is everyone okay with why domain and range is all real numbers? Okay, if we look from left to right, we know those arrows are going to go on forever in the left, in the negative direction, and in the positive direction. And then if we look up and down for our range, we know this is going to continue to fall, and this is going to continue to rise. Okay. Great, that was really nice teamwork. Are there any questions on the warm-up problem? I know some of you had maybe all of this information down. Some of you had only a few of the pieces written down. Are there any questions on the ones that maybe you didn't get to and we just wrote up here? All right, so this is what we're going to do. We're going to go over 2 things today. One of them is called average rate of change. And then the second is the only parent function that you don't know on your chart. Okay? So, first of all, rate of change. When you hear the word rate of change, what do you think of? What do you say? Slope. Would you agree with Caroline? Rate of change, you think of slope. Okay? Now, what kind of functions do we measure slope with? Linear functions. Lines have slope. If I gave you a polynomial, does a polynomial have slope? No. When I say polynomial, x squared, x cubed, x to the 4th, those graphs don't have slope, but they have special characteristics. Now, slope is really nice, and we can do a lot of cool things with slope. But only lines have slope. Okay? So we're going to talk about what's called the average rate of change. Okay? So if we have a function that is not a line, we can calculate the average rate of change, which is basically the slope of the secant line. Okay, so this is what I'm going to do. Okay. Stop writing for 1 second. Raise your hand if you know what a secant line is, or if you have an idea.
Isn't it, the secant is when it's like, there's like a circle, and it just touches like the edge of the circle at one point, and that's it. Or like, the side of the circle.
Okay, how many times does it go through the circle?
It doesn't go through it, it just touches the side.
It just touches the side. What were you going to say?
Does it cluster at 2 points?
Okay, it does. You were thinking of a tangent line. Tangents hit once, secants hit 2 times. Okay, we're obviously not talking about circles. So when I say a secant line with an equation, we're talking about it's hitting our function 2 times. Okay? So now you can continue.
So like the diameter of the circle would also be a secant.
Technically, yes.
Like if it's something
Mm-hmm. Okay. Gabe, how do you find slope? Mhm. Okay, explain it to me in words. Like when you say slope, what word? Rise over run. Okay, so when we're thinking of that rise over run formula, our y difference of y's are in the numerator, difference of x's are in the denominator. Okay. We are finding the slope between 2 points, but these 2 points are on a curve that's not a line. Okay, so it's not the constant rate of change, it's the average rate of change, because functions that are not linear do not have slope. Okay. So here's the example that we are going to do. X squared minus 2x plus 8. Okay? And I'll go ahead and tell you what that graph looks like. We know it's a parabola. I'm going to tell you that I know it looks like this. Okay? So what's happening is we have a line going through the points at x is 1 and x is 5, and we want to find the slope between those 2 points. Now, if we want to find slope, what do we need to know? We need to know the y values. Okay? How do we determine the y values? We're going to plug in our x values. So, please help me out. I need you to find f of 1, and I need you to find f of 5. So we'll split up. We'll do some teamwork. If you sit in a pod with an even number, please find f of 1. If you're an odd number pod, please find f of 5. Your pod numbers are above you. I think maybe you should know what we got by now. Okay, pod 4. Can someone tell me what they got for f of 1? 7? Someone from pod 7, what did you get for f of 5? 23. So this is what's happening. We have the 0.17 and the 0.523, and we're calculating the slope of that line. Okay? Slope, rise over run, change in y over change in x's. So our y values, 23 minus 7, our x values, 5 minus 1. 23 minus 7 is over 5 minus 1 is, okay, so 4 is our average rate of change. That's the slope of that line connecting those 2 points. So on average, we're changing 4 y units per 1 x unit. That's what that's saying. Okay, it's not a constant change, but on average, that's the change between the 2 points. Okay? Basically, you're finding slope. All right, are you ready for like the craziest graph ever? Okay, the greatest integer function. If you looked at your 8 basic function chart, you didn't know what that was until today. Okay, this is the graph. Y equals greatest integer. This is greatest integer function. And I will define what it means to be the greatest integer function, but you need to know what the graph looks like. It is important that here at 0, 0, you have a closed circle, and then here at 1, 0 is an open circle. A closed circle at 1, 1, connecting a segment with an open circle at 2, 1. A closed circle at 2, 2. An open circle at 3, 2. Okay, and those segments in between. What does this look like? Looks like stairs. You may hear people call this the stair function or the step function. Its name is the greatest integer function. Now, what's the domain of this? It is all real numbers, okay? We have a bunch of jumps, but if you look, we have x values everywhere because here where there are open circles, right above it is a closed circle. So there is an x value there. And since we have an open circle where there are closed circles, it's still going to pass the vertical line test to say, yeah, it's still a function. Okay, that open circle is the same x value as a closed circle, and so only one of them really count for the domain. Okay. Okay. So when you see that symbol, it kind of looks like the double absolute value, right? When you see that symbol, this is what it means. It means the greatest integer less than or equal to x. Write that down, and then we're going to think about it. The greatest integer less than or equal to x. I'm going to switch back to the graph 2 here pretty soon. Remember, integers are numbers like -1, -5, 2, 3. Basically, we don't have any decimals or fractions. Okay, integer. Okay. So if we're saying the greatest integer less than or equal to x, we're basically rounding down to the nearest integer. Okay. So if I say, if we wanted to evaluate the greatest integer of 3.2, what's the greatest integer less than or equal to that number? 3. Right? If we have the greatest integer of 3/2, we would evaluate that to be 1. We're basically rounding down to the next integer. Okay. If you look here, right, any number between 0 and 1 is going to get rounded down to 1. And then when we hit 1, the greatest integer of 1 is itself. If it is an integer, it gets to stay itself. Okay? So that's why we have these closed circles here. And then in between two integers, everything's getting rounded down. That's why we have that stair. Yes.
So if it was like 3.7, it would still equal 3.
Yes. Great question. This is what she asked. If we had 3.7 inside, we would still round down to 3. Okay. Here is 1. What if I gave you the greatest integer of negative 1.5? Negative 2 or negative 1?
Negative 1 is greater than negative 2.
Correct. And we want to round down to an integer less than or equal to what we have. So what's the integer less than negative 1.5? Negative 2. So those negatives, we're going to have to think a little bit, right? What's the greatest integer of 3? 3. Okay. Is that a fun function?
Why the heck would anybody create that? Somebody just wrote that instead.
Well, if you think about, like, has anyone ever been to a parking garage?
No.
Okay, so it says if you're here for, this amount of time, you pay this. If you're here for this amount of time, you pay this, right? It's like by hour intervals. It doesn't matter if you're there for an hour and 7 minutes or an hour and 59 minutes. You're still paying the same amount. You see what I'm saying? Situations like that. Okay, so this is your homework, which is on your gold sheet. Okay, this is going to be attached to the assignment from last night, and I will answer all questions from both assignments Monday. Okay?
So can we do it on the back?
Oh, yes. And since I don't physically collect your homework, you can switch as many assignments together on pages as you want to, unless that bothers you. Okay? But I'm not physically collecting your homework like Mr. Griebel did, so you can have, like, all of your homework in a notebook if you want. All right? Okay, so what I need you to do is clear your desks.